Thank you for having me. So the topic today will be about curving rules and passenger comfort. So as a background for why we're studying this topic, or why we do a research about passenger comfort and curving rules, as you know, the railway standards have some engineering requirement or rules, what we call it like curving rules, that governing the design of a curve or transitions. And these rules generally have not been changed for many years now. Now, this rules basically controls the running of the train in terms of basically the curve design in terms of count efficiency and the rate of the count deficiencies, and the installed count and the value or the level of the installed count and the rate of the change on the installed count as well. And also it's covering the speed of the train over switches. Now, this is done for safety purposes and to get more safety performance and basically have more better passenger comfort. Now, however, there is a current requirements basically, the current requirements of these rules has been defined based on empirical basis under condition which is not available now in the network. These has been defined 30 or 40 years ago. Basically the standard of maintenance has been changed. The vehicle or the rolling stock has been changed as well. So this pushed to some research questions about these rules. Some of them like what are these rules and what's aiming to manage, and what's the scientific basis behind these rules, and do we need since there is like evaluation and development in rolling stock, do we still need these rules, or basically we need, but can we relaxing these rules and having or we can just optimize them? So in order to answer some of these questions, currently we have some projects with two projects with Network Rail. The first one related to the Transpennine route upgradation, which is the aim of this study is to look into the ride comfort and track forces when adopting exponential track design values, and that's mean increasing the maximum applied count from 110 millimeter to maximum 180 millimeter, and increase the count efficiency from 110 millimeter to 150. Also, we have another projects looking into the passenger comfort and transition and curve, in curves and transition, mainly in transition. And the aim is to have a better understanding the relation between the passenger comfort and the track design and geometry. And both projects. In these both projects, we looked into the ride assessment methods defined in the EN standards 12295. 9. We looked into the main, within this project, we looked into the main ride comfort within this, it's like some indexes defined by the standards, and according to these indexes, you can see this, it's kind of defined that your riding is comfortable or not. For example, for the main ride comfort, you have a 5 minutes analysis window. You will have a single weighting index, calculate based on the lateral acceleration and vertical acceleration. And what you get from it, it's one value. And based on this value, as I said, you can say this is basically a comfortable ride or no. Also, we looked into, within these two projects, we looked into the continuous comfort indices, and this is having a shorter window time, 5 seconds, and also they have a weighted indices and is calculated from the lateral and vertical direction acceleration. Again, you can see they have some limits, and based on these limits and values, you can say it's comfortable or not. Also, within the standard, there is another index to describe the passenger comfort called discrete events. And it's basically a satisfaction value based on the relation between the steady state acceleration and the peak-to-peak lateral acceleration, as you can see in the bottom of your, to the basically left of your figure. You can see as the values for the steady state lateral acceleration and peak-to-peak lateral acceleration increase, the people who feel uncomfortable, or the percentage of the people who feel uncomfortable increase. So this is the percentage of the passenger who say they are not comfortable with the ride. Also, within the standard, you can have a comfort index on curve, and especially this is the PCT, the comfort index on curve transitions. And this is specific on the transition, and it's also a relation between the steady state acceleration, the transition, and the rate of change of lateral acceleration, the jerk. And you have two values, basically one for standing and one for seated. And you can see as like the people who feel uncomfortable or dissatisfaction, the percentage of them increased when they are standing compared with the seated. So within these two projects, we looked into to assess the riding comfort based on different conditions, and we used all the indexes defined within the standard. So taking you in some of the output from our study, this is related to Project 1, Transpennine roads upgrade, mills in section the mills Platting example. So as you can see from this example, you have two design curves. One is the existing, which is measured by a measurement train. And the aim was to modify this design into a different design and increase the speed in order to make it like the train going faster on these curves, and to study how this will be affect the passenger comfort and also the forces. As you can see, the top figure showing the curvature, 1/kilometer, and the modified the modified design is reducing the curvature from 5 to 3.2. Basically, also within the modification, this will suggest to increase the cross level from about 60 to 150, and you will increase the speed as well, so that will end increasing the count efficiency. And you can see these will have some effect on the lateral acceleration, where the lateral acceleration will be increased, as you can see from the red line. Now, this increase in lateral acceleration will affect the ride comfort. So still we are in the Project 1. You can see in the top figure, this is as example, we test several routes, but this is like one of the routes we are looking at. You can see the differences between the existing and modified, as you can, the result for the ride comfort, as you can see from the table. So these are with, the simulation was done with using irregularity and non-irregularity track, and irregularity is like you have a real measured alignment from network rail. So you can see by moving from the existing design to the modified design, there is some slightly increase basically the riding comfort become more uncomfortable. Although when you have non-regularity, which is like an ideal situation, it's still all within the accepted limits. Also within this project, we looked into how the relation between the ride comfort and the maintenance limits. As you know, in network rail, they have some, and basically in the standard, you have some limits related to the peak lateral alignment and the speed of your vehicle. And as the peak lateral alignment increase, you need to have some actions. So, like example, between 51 and 75 mile per hour, you don't need to do anything until if the peak was within 13 millimeter. As the peaks increase, then the maintenance start. We need to do like take an action, define the maintenance plan. It's based on the amplitude of your peak lateral alignment. Now, in this study, we try to take a major track with a fault, and we start to increase on this fault, the peak of that fault, and start to calculate the acceleration from them, and basically look into the ride comfort. And you can see from the figure down the continuous ride comfort against the peak lateral alignment. So pretty much until you reach to 25, you will become the ride test less comfortable, and this is you are crossing the plane limit, the plan maintenance, which is in orange. So as a conclusion from this study, and it's have like a lot of conclusion, I just picked two of them. By moving from existing to modified, you will have a track shifting, and the rail or the forces on the rail will be higher, and but basically this will lead in, if you adopt such changing, you need to look into your maintenance and inspections in more detail. However, when we look to the riding comfort, you can see that there is no huge changes between the comfort itself, looking to the table. And this is what lead us to the second project, the riding comfort on curve and transition. Basically, when you look at these values, it's a values, but there is no physical, let's say, physical meaning about it is not understand. If someone told you can increase the speed of the train by 10, let's example, by 10 miles per hour or 50 miles per hour, but the passenger comfort will be moved from 2.8 to 3.2. You kind of, what the meaning of it, what the physical meaning, how the people will feel inside the train. This is what we are doing in our next study, which is the assessment of passenger comfort on curve and transition. And the aim of this one is to challenge the passenger comfort limits defined by the standard 12299, and particularly looking into the PCT, the comfort index on curve transition. Now, we did and within this study, we did simulations and experimental tests, and using our motion simulator, THOMOS. I will explain THOMOS later on, and showing the capability of THOMOS and the application of it in the end of the presentation. And we did design a range of curves that have a different range of PCT values. And ideally, we need to identify if there is any scope to relax the current UN requirements. So, as a methodology, we did kind of, it's not like probably clear figure, but what you can see there is the steady state lateral acceleration against the rate of change of lateral acceleration, and what you can see there is the PCT index. And as I said, this is the percentage of people who feel uncomfortable when they are riding within that particular journey. Now, we did each point from them represent one curve that we simulated, and you can see for the seated, the percentage of people who feel uncomfortable increased from 3 to 23% when we start having a high can deficiency. And for PCT in the standing case, which is the bottom figure, the simulation starts with 13% people on that particular curve, and as you increase the can deficiency, the people reach to 64%. They don't feel comfortable. Now, as I said before, this is what you get from the equation, but how this is in reality look like? If you just, as I said before, if you will increase the speed of the train by 10 or 15 miles per hour, and you will increase the capacity of transportation, you will increase the passengers, the train, you can put more train on the track. The percentage of passenger moved from 30 to like 40%. What does that mean? I mean, is it acceptable or not? So this is what we are doing now in our study. We did create 20-minute demo routes that we will feed it to have a curve and straight route. Track, sorry, and you have like left and right curves, a wide range from the PCT values that's shown here on the figure. Also, we will ask 40 participants to go into THOMOS and voting their riding experience by showing giving their feedback. And basically, we will repeat the scenario to compare the consistency of the response that we obtain. There is a questionnaire asking about the age and how often they are using the traveling. They travel on the train, and how their occupation, what their occupation as well. And then basically the output from the study, we can have some statistic analysis and to see if there is any scope in order to relax or to do like further investigation in order to relax the requirement in the standard. So just a quick presentation about our motion simulator, THOMOS, train Hi-fidelity on-board motion simulator. We can have a full motion replay based on the vehicle dynamic simulations and imager data from the train. We can simulate any vehicle, a metro, a tram, a high-speed vehicle. We can do any simulations and getting the output of the accelerations and feed it into THOMOS, and the THOMOS will follow the simulations basically. We can put up to 4 seated and standing passengers, and we have like a scenery about 160 kilometers, so you can have a field scenery or a city. We can control the environment day or night. These have the sounds of the diesel and even the vibration of the vehicle, diesel or electrical traction. You can have also the effect of sound and vibration as the train go through switching and crossing, rail joints, and some braking noise. We can control the temperature, and as you can see from the picture, you have pretty much a similar layout of a typical train here in the UK. And we can reconfigure this layout, and we also have like a video and sound recording as well. So for you, if you think about any projects that will be suitable for or any collaboration in the future, so this is like one of the some of the applications that THOMOS can do. We can demonstrate a vehicle dynamic simulation results a lot of time when we do any wheel rail interface or any dynamic riding comfort, we just basically we just give numbers, and by doing the simulations we can have the feeling. We can study a ride comfort for seated and standing passenger. If you have a new design for the suspension or track design, we can test it as well. And basically, I will not go through it all, but we can basically doing like look into the passenger response to emergency braking as well, and investigate the trade-off between the suspension design and track geometry. So basically, if you have any new design and you want to test the people, how they will feel, the passenger comfort on this new design, we can do that through THOMOS. So this, just before I say thank you, this is the video for THOMOS in action, using some of the simulated curves. And this is how it's look like inside the THOMOS. We can have a scenery, and as I said, you can simulate the train going up to 360 kilometers per hour, and we can simulate any curves or any condition basically, and people, putting people inside, they vote if they feel comfortable or not. Thank you.